So this is some work that was done with collaborators, some of my co-authors and KAUST as well, which I like to point out, and also some funding from NSERC Canada. Yeah, so in outlining some of the topics I'd like to talk about today, if this advances forward.
There might be a lag between when you click and.
I see. Okay, gotcha. Okay, great. So an outline for today, I'll go over a quick introduction of inverse problems in geology, of what type of data we're looking at, and generative AI in general as a tool for reconstruction in other domains as well, and using simulation as a data source for training also in some other domains outside geology. Then we'll look at simulation methods for geology. So how do we generate diverse 3D models with a case study on a software package that was developed for this research, StructuralGeo, or also known as GeoGen, and some of the challenges and limitations in doing so. And then we'll take a look at the generative modeling side of things. So this is deep learning, it's probabilistic machine learning, and then we're looking at conditional and unconditional generation. So when you have some data, and then when you don't have any data at all, you're just trying to make general models. And then an experiment with ensemble sampling from such a model. And then I'll talk about some future directions for this work and conclusions. So today I'd like to talk to you about a problem that exists. There's many people in this room that are working on this problem, and it's a hidden Earth. So we have a lot of either sparse or indirect observations of the Earth itself, of the subsurface. So this could be things we're looking at boreholes or direct sampling, so of geochemistry on the surface, for example. So these are true observations, but they tend to be sparse or incomplete, like in the case of boreholes, for example, and expensive to acquire. On the other hand, we have complete surface maps that we can make using potential field surveys like gravity or magnetics, as well as remote sensing. So this is continuous coverage, but it's also an ill-posed problem when we want to try and invert for the 3D structure below the surface. And we run this issue of dimension reduction from a 3D volume to a 2D signature on the surface that contributes to that. We can look at structural mapping on the surface as well. So this is the lithology, observations like strike and dip. Again, this is heavily biased towards surface outcrops, and it's an ill-posed problem when we try to do depth continuation with that. But the goal between all these different data modalities here is we're trying to reconstruct an accurate model of what is beneath the surface, yet we don't have any ground truth examples, over a large area of what has actually been dug up in place. So there's a lot of expert inference over the years that has gone into this work to develop models of what exactly is happening beneath the surface of the Earth. I'm now going to look in some other domains to inform deep learning a bit more as a field and some of the things that we can do with that. So looking at vision and video, we have a similar problem where perhaps we have one or more modalities. So this could be a text or an image input. Any of these image generators maybe you've tried using, and you can say, hey, adjust this photo, change this with it. So make this model more realistic from this frame on the previous slide, or add a large fault tip, for example. And so this is taking the original image, and this text is conditional information, and basically doing almost like an inverse problem back to the image that meets those qualifications there. So quite similar, and you can also get multiple reconstructions from this. There's not only one true reconstruction. To do this type of generative AI requires an extremely large amount of training data. So for these vision models, that's been done by scraping the internet for data and text pairs. We don't have that same sort of convenience when it comes to 3D structural models of the Earth below. I'll point out another application in video. This one is interesting, I point out, because it's coffee pouring. So this video model was never actually trained explicitly on physics, but yet it's capturing some of what you would expect from fluid dynamics. It's also capturing some things that aren't quite correct and seem a bit uncanny, like this splash that comes out of the cup with seemingly no source. But this is an example of what these technologies can do with enough training data. Taking a look at a different field, this is robotics and reinforcement learning. So this is something that I worked on in engineering physics, for example, but we can actually enhance our training of a deep learning model for control of a robotic system by using simulation. So in this case, maybe we have one version of a robot, and we only have that specific version of it with its current system dynamics may change with its friction and the way the motors are operating over time. We also can't scale this learning. So if we want to train it through many different environments or many different possible scenarios, we're constrained by having this one single robot for training. So oftentimes what's done in this field is you train in a simulation, and you can experiment with different types of system dynamics. And this actually functions quite well to either augment the training, or you can actually completely train in simulation, deploy the model then on the real robot, and have it functioning in the real world. But there's oftentimes a gap between these two. So this is known as the sim to real gap of the difference between your performance in a simulation versus the real world. But this is a good example of using simulation data as a surrogate, let's say, for real world training. And the goal with all these is to find a mapping. So we want to get a parameterized function, thetas are parameters, and we have an input x, for example, and from that we get an output. It may be a probabilistic output, like many different reconstructions. That's what these all have in common. And in a lot of ways, this is the same type of problem that we're trying to tackle as well when doing geological inversion, where we have some knowledge about it, x, and then we have a parameterized model of some sort of how we're going to do that reconstruction. So the previous methods were all data-driven. They relied a lot on having examples that are mathematically encoded. For example, pictures have pixels in them that have precise values for each one, and model can ingest this. It gets a bit more challenging when it comes to geology, because a lot of our knowledge, in fact, would be like from these excerpts in a structural geology textbook here, where we have folds or we have lithological features. We've built these models through observation on the Earth's surface. We have like a fault, for example, and a good concept of what these look like in a sketch. But these images here aren't necessarily the mathematical encoding of what these concepts really mean and the diverse instances that you might observe for them. So what we want to do is to find a way to encode these abstract geological concepts like folding and layering into synthetic data or some type of mathematical form. And to do this, we can simulate 3D lithologies in order to give examples to a model to train from, where it couldn't directly train from these textbook examples, for example. So the idea here is to incorporate geological principles into the simulation so that the generative model will learn this, and then we can then apply this to some problems with inversion. The overall map for all this is we have here geological knowledge. So this is textbooks. This could be those sparse or indirect observations, and this wider picture. And we want to try to encode all this. We use the geological simulation as a mathematical encoder to get these more abstract ideas into actual full 3D reconstructions or samples to train from. We train the generative AI using this, so we learn some model parameters or weights. And then an important part here after is to point out is once we've done this, and we've learned some sort of probability distribution indirectly over what geology is supposed to look like, what's plausible geology and what is not, we can then discard the simulation completely, and then we just work with the generative model for some applications. What are those potential applications? I'll point out this is a classic painting here. The girl with a pearl earring goes back to 1665. And it was really exciting at some point in vision models, at least. They tried this experiment of doing outpainting. So you have a painting from some historical period, and you do this outpainting here, and it reconstructs. Some people call this like a hallucination, but it's basically a probable model of what was around outside the painting. And so you can see it matches the period from the painting, and there's a lot of things that are realistic and plausible about it, but it's not necessarily the ground truth. But taking this this type of reconstruction image space or an image problem, for example, we can see the applications that it has. That you can go from low resolution images to high resolution images, for example, through a generative model, where it's been statistically informed by many different examples that's seen to actually do reconstructions that are plausible and multiple different ones. So this is an inverse problem going from low to high resolution. We can do in-painting, so take all of this statistical inference that's gotten from a simulation, for example, or from data-driven examples to fill in a missing piece of data. There's the out-painting task, which I mentioned before, and then we can do image to image. So something I'd like to point out, and this is a good example for the in-painting here, is sure, like we're not certain of what exactly should be in that spot there, but with a model that's been trained on many images, we would almost certainly expect for there to be a head there or some type of continuation of human anatomy, for example. And if we were to sample it many times, we could notice that in each of the examples, it does have a head there. And so we could start to get this type of information of the different types of things in this box rather than just the one single example, and gain a bit more of an understanding of plausible reconstructions in this way. Now moving on to our research from this recent paper, we're going to look at the case of synthetic geology, specifically looking at structural geology. So we're looking at lithologies or rock types here. This is not geophysical data. This is like categorical like rock lithologies here. And our goal here is to do the problem of reconstruction from surface and borehole lithologies as shown here. And so for part one, I'm going to look at this task of building a simulator for such a project and how we're going to encode geological knowledge into a trained model. So this is the GeoGen synthetic dataset. As part of the work for this research, there was identified a need to make a very fast simulator because I'm talking on the scale of millions of samples and they're 3D volumes, and these can be quite expensive to generate, certainly by hand on someone doing them manually on a computer. So we want some type of automated generation. This can be quite costly in practice. There are prior simulation models that I'm showing here to point out. There's GenPy. This uses scalar fields. It has these implicit surfaces in it. That's one way of modeling. There's Naughtyverse, which has been around for a very long time. It makes these lithological blocks here. Notice there isn't an air rock surface in these ones, but this is some prior work that exists out there. Naughtyverse is originally written in C, I believe. And so one of the goals with this too is to find something that's maybe native in Python code, for example, which is where a lot of machine learning libraries are to get this type of direct interfacing. So this motivates building a new modeling framework that's going to be quite quick to generate the samples with. So the modeling framework is we define some different geological processes. So you can see here a sedimentation is being added to an existing model, for example. And we can parameterize these, like the depth of the sedimentation, for example, what sort of lithological categories would be in there. Once we have these processes that are defined that a human would be able to fill in with parameters, now we want to look at doing some type of randomization. So constructing a dike, for example, that has the average width that's known for a certain region and sampling that from a random variable to construct many different dikes of different widths, for example, or randomly sample the strike and the dip and so forth. So once we have these random events, we then sequence them together to form different complex lithologies and different structural models here in 3D. And then on top of all this, Torch data set, that's PyTorch is a library. So this is basically something that's going to extract the examples from it and prepare them like as data for a machine learning model. So I'll point out too, actually, with this, something interesting with the simulation is the very bottom layer of it you can actually use just like for human construction. So there's actually inherent in this not just a randomized simulator, but actually a modeling package built at the base of this pyramid. So looking at modeling package, the stage of the computation, in order to save time, this is using a Lagrangian method. So what this really means is rather than, we want like a nice regular cube as shown in the top right here. So we want that in present day for our final data samples in the same way that when you have an image, it's not all weird and distorted. It's in a nice square or something like this with regular pixels. This makes it a lot easier to work with. However, the geology operations are going to deform this sort of cube. So starting with that would get deformed rather quickly. So instead we work backwards from an initial mesh grid. This is essentially a shortcut, or let's say a limitation in how the data is actually processed, but it does gain a lot of speed, is that we don't do deformations like faults or folds conditioned on the actual type of rock strata that's in there, but rather on an empty mesh. So there's an unconditional step of tracing backwards through time. So that's shown on the bottom of the screen here. You can see the gray becoming more deformed going back in time. Once we reach the start of the geological history and we've inverted all these operations, we then paint in the sediment layers on these sort of sample points that are being tracked around. And now we can work conditionally. So we can work conditionally on what rock layers are already in there when we're doing sedimentation or unconformities and operations like this. And we simply undo the operations as we're moving back forward through time, putting in these types of sedimentation or unconformity events to get back to the present. So this has advantage of speed, where we're not necessarily doing a pure physics-based simulation with those types of faults, but rather painting in the expected effect from a fault. So what that looks like, this is a point cloud, and far back in history, it's quite deformed here, and these are all the different sample points. And as it's moving forward in time, there's new types of layers that are being painted in, and it's slowly returning back to this final regular grid that we want in the present. And now for these random variables, so in the package it's called the geo word, but this is basically a concept. If you have a fault, for example, it becomes very difficult to generate randomized models that don't go out of control if you don't have some type of constraints. So there's this trade-off. You want to explore diversity in the models, but at the same time, you don't want them to become so diverse that they no longer represent plausible geology. So in order to constrain this better, it's a much easier task to look at it as individual events. So you can define something like a large fault, which will have a range of amplitudes. So it's not a specifically defined large fault. It's that the amplitudes are within some sort of range and it has some type of orientation. So these are like fuzzy geological operators. The concept here is to have something that's not strictly defined, but rather a type of event definition that we can then reuse in many different histories that will be within this kind of controlled regime and not be out of bounds in terms of plausibility. So we sample these events using like faults, folds, and shears. We can introduce correlations between different types of events. These are geological snippets and small events. And by organizing these snippets one after the other, we then get our models. So we can have an initial strata and then a fold, a dike, and a fault in this sequence. If we change the sequence of these events, it'll generate a different model. So we can also generate diversity based on the ordering of the sequence and also on the length. As we add more and more operators in, the model becomes more and more deformed and there's more and more activity in it. And so this is a way to simulate geological age. For example, a much older sample of the crust, we might expect there to be more deformations in it in general. The sequencing is done using Markov sampling schemes. So this is a simplification to make it tractable, the problem for the simulation. So basically, depending on the previous event, we have a row lookup. So if my previous event was a fault, perhaps it's more likely that there was a fold that happened after that, compared if the previous event was a sedimentation. So there's some amount of guesswork, some amount of reading literature, but really some of these probabilities are not very well defined in the real world. So this will lead to actually to a limitation of small, but also an interesting future research direction. So we have some weights on how we're going to sample these. And then there's the early termination event. What this does is there's a chance of the geological history ending a little bit earlier, and this will be a younger geology. So we get this exploration both of different geologies and the events that have been sampled, and also in terms of the age of the sample from the subsurface. Looking more at this, the whole picture in the pipeline, basically we can just request batches now of mathematical examples of what geology is supposed to look like, and we simply get our tensors back, going through all the different things that we talked about, constructing these histories and then doing the model generation computation. The advantage for this is we can do unlimited samples because we're going to need a very high number of them, and we don't need to store them on disk. So this is done in the order of 5 to 10 seconds on this laptop, for example, to generate one sample like at 128 cubed. So these are larger volumes and it's generating them quite quickly. And so rather than saving them to disk and having to pre-compute everything, we can generate them on the fly and then feed these in as examples to the machine learning model. So that really reduces the disk storage because these are large tensors or these would take up a lot of storage on a disk. And then we can also customize it. So these transition probabilities and these random variables can be adjusted regionally, for example. So you could imagine tuning this to some type of problem application within this framework. So what the models look like, here's an example of 25 of them. So they look different from each other. There's many different features. Some like would be a younger geology like down here. But I'd like to point out some of the limitations. So this is an exploratory work. So with improved model fidelity, with feedback from experts on geology, for example, of how to improve these sorts of features, we'd expect as we get more and more close to approximating real-world geology that we would get better results from downstream. And then another interesting area of research, and it's been continued with some of my collaborators at KAUST, is this idea of matching the forward observations. So we can see the surface on these models, for example. So the models generated from the simulation should ideally be matching in distribution to what we observe on the surface on Earth. We do have these indirect observations from which we can check of how well we're doing in terms of reproducing real-world geology. If we have some mechanism to do this in an automated fashion where we could tune these parameters and these transition probabilities in different portions of the simulation, this would turn into much more of an automated pipeline, let's say, and even less human intervention required to get that model fidelity. Okay, so that's the simulation work. Now we'll get on to some of the fun stuff here, the generative modeling with flow matching. So there's going to be a bit of math and some machine learning background on this. But I've kept a lot of it visual here for today. So we're looking at the second part now. We assume we have very rapid samples, and we're going to train our generative AI. Okay, looking back at the inverse problem, we have a forward operator, a model, and then some noise. We could maybe characterize that as being Gaussian, epsilon, and that gives us our observed data, D. We do Bayesian probability here in order to try and find the most likely model given our data here. So this is the maximum a priori estimate. So note this gives one single model, and really the direction of this research and the question that we're trying to explore is rather than this is the single point that would be sampled in this deterministic way. We have some flexibility on how we're going to specify our prior here in this system, but when we minimize this problem, what we get is one reconstruction. And what we want to do is to find out more actually about the space of all the plausible reconstructions, because as you can see, there might be some other basins or plausible geology that's around there. And that's really the benefit with using a generative AI, is that you can actually produce many different reconstructions and not only the most likely one. Note that that's within a probabilistic framework. So sometimes regularization isn't explicitly said that, shown that way, but it's an interpretation of using a regularizer is through probability. Now, if we want to learn the probability of all of these models from the simulation directly, we run into an enormous problem. And that's if you parameterize some sort of function to learn a probability, you don't get free rein to learn any type of function. The function, in order to be a valid probability function, it needs to integrate under all the area underneath it to a sum of 1. Like you must have a total probability of 1 with any probability density function. So this is the partition function that normalizes any learned function, and computing that partition function becomes very intractable as we go up to higher dimensional spaces, like these geological models are residing in. So the solution to this is similar, if some of you have heard of diffusion models before. Those are based on SWOR, which takes a gradient. In a similar way, we can do flow matching. This takes velocity. So the key thing here is there's a derivative that happens, and it magically gets rid of this partition function so we don't need to deal with it. We pay a price for this, though. We don't directly learn the probability model, but we do learn a way to draw empirical samples. The way that we do that is we sample from a known distribution, like this blue Gaussian in the middle, and think of this red as being a more complex probability distribution, like all the models that could be generated. And so the goal here is if we can push from the blue to the red, then we can just empirically sample from plausible geology or in a conditioned manner. So what that looks like, of pushing a probability distribution, this is taken from a paper here by Lippmann, is you can imagine almost like an elastic membrane and deforming that initial probability distribution with this velocity field into the much more complex one. And that's the way that we're going to learn it. So this is the general framework. The reason I actually bring up flow matching here is it's a surprisingly simple algorithm in its implementation. And so we basically are going to stochastically sample from our complex distribution, our simple Gaussian here. We draw lines in between the two. So this is a stochastic element, and you can see all these green fibers are making a network between it. The actual true velocity field that's going to give us this push through, like shown on that membrane, is where we minimize. If we guess what the direction is to go in at any of these points, we want to minimize the error in our guess. So our machine learning model is parameterized with theta here. And then we have these VT, which are the true velocities as represented in the direction along these green lines here. And we minimize that overall time. So this is at time 0. And at time 1, moving through this velocity field, we'll get to our target distribution. So looking at that, this is a 2D example here. The algorithm goes through, we draw our Gaussian here in blue, our target distribution red, we draw one of those green lines across the two. We randomly sample a time, here it's 0.6, so we're 60% of the way along. That's our current position in the model. And then the derivative of that will always just be x1 minus x0, so the direction pointing along this green vector. And that's going to be the input here, and that's what our model learns. So you just randomly sample through in this manner, and you just keep training through many, many different examples generated on the fly by the simulator. Now a question, what does categorical velocity mean? Categories are discrete, so there's not really a velocity between them. You're either one category or other, and they're not necessarily ordered. So to deal with this in the paper, we simply lift the categories up into vector space that is continuous. So if you have 15 categories, you could kind of go into a 15-dimensional space. And you can move around continuously there. And then when you get to the end of the sampling, you just move essentially to the nearest neighbor category. Like, so you might be at category 1.1 or something, or the closest category that you are to is 1. You simply snap back to that at the end, because ideally in the generated samples, they should be very close to a single discrete category. So this is an animation what that looks like. We take a lot of samples from the Gaussian and we push them forward, and then we can draw new samples from geology. Now, doing this conditionally, we throw in a new objective here where we do have some forward observations like the surface data and the boreholes. So we put this in as a conditional on the model. So the learned model now actually can take that information too. So this gives a lot of clues about where it needs to go on that target distribution by having that forward data observation. It's no longer an unconditional flow, but a conditional one where it has a good sense of where it's supposed to be going. And what we're learning indirectly now is not just the probability over all geology, but the conditional probability given the data, which is what we originally used Bayes' rule for. So this is a direct approach end to end. We add in a new term. This is our misfit basically from before. We predict where the model flow is going to go to at the end of its trajectory at time 1. And we look at what our actual observations are. And the penalty for the difference between the two becomes more and more severe as we're closer and closer to the final time equals 1, where we're going to be frozen in place with the model that we get. So this T term here basically scales that up. It's like a regularizer in a lot of ways. So we add this in during the training, and this enforces the model to sample with the correct surface, geometry, elevation, and all the lithologies and the boreholes as well. We put this through a machine learning model. It's the architecture of the model. There's many different choices that could be done. What we use in our research is convolutional layers, attention blocks, and this is a UNet, so it looks at that information over multiple scales in the feature space. We also need a way to insert these time and data points into it, because recall we're sampling between time equals 0 and time equals 1. Yeah, so this is the full pipeline. You can find in the paper, it's everything together. We take the simulation, generate our sample. We find our forward information, so we can make some random boreholes and surface data. This is a contribution from the paper. We actually take the adjoint of it, and this just opens up whatever observations we have into the same dimension as the model space. And then we embed all this into the continuous space, and this is the machine learning model. So it gets the information on the forward data, it gets this time embedding. We integrate that through time, through this velocity field, and we just push it forward to time equals 1. And so doing all of that, what does that look like? This is unconditional generation, so we don't have any forward data. And you can see, maybe the animation is not on the screen there, but that's the final result. But it comes out from this sort of noise where it's undecided on categories, and then the final sample becomes more decided. It does look a little bit different than the simulation examples, but we can see those lithologies in there and the layering and a lot of the original concepts that we were trying to encode in, like this vertical dike placement right here. It does take time to train on GPUs. Generative AI is expensive. The electricity on this one wasn't that bad because I found out electricity is really cheap in BC. So go nuts on generative AI here, I suppose. More interesting is this conditional generative model. So this is end-to-end solution for the forward inverse problem. And what I want to point out here is that there's 3 different examples now based on this conditional data. And you can see that the vertical dike is different in each one, but there is a vertical dike in each one. And there's some cross sections just so that you can see inside the model that there's some complexity that's going on in there. We can sample many different conditional models then, and then ensemble them together to start to develop a bit more of a theory about what's going on and how far maybe a feature extends. So this is isolated, just that vertical dike, and this is the true vertical dike. And so boreholes didn't sample all of it, but there's probabilistic regimes in terms of how many of these ensemble models and how far they're sampling. So by and large, all the models will sample in this darker orange here, and with lower and lower probability, they will sample to a higher extent. So you can get more of a feel of how far that feature might extend in this way by sampling many times from the conditional distribution. So these are some different dike reconstructions based on this dike information that's there. Okay, and finally, some conclusions and future work. Some things that I would like to see would be, of course, more explainable constructions. So it's nice when we have these conditional model constructions, but there isn't necessarily an explanation of what the model is seeing and why necessarily is constructing a feature to some extent. So there's some interpretability questions at play here. In other domains, like in medical imaging, you can do things like attention heat maps and different mechanisms that tell what part the machine learning model is using as information in order to reproduce that construction, of which areas are the most important, for example. So this is an important area of work in the future. Another area we talked about at the start, but all this data is multimodal. So there's many different types of data that are out there. So if we could find a way to combine not just the surface and borehole data, but maybe some other types of data to turn this more into multimodal conditional data at these points where the model has access to the forward operator. And also to not have to fully retrain this model. For example, if we change our data modality from surface and boreholes to gravity, for example, then we shouldn't need to retrain the entire backbone in the model. Really, all that we're changing actually is the data input for the forward problem. And then finally, an interesting area of research, I'm working on this problem right now, is model scoring. So it'd be nice if we had an estimate of which models are more likely than others. So far, I've only shown a way to empirically draw new models from the distribution with no indication of which ones are more probable and which ones are not. So if there's a way to backtrack, for example, to try and find this information, then you could have multiple reconstructions with them basically being tagged in order of which ones are more probable than others. And finally, I'd like to just share my vision. When it comes to AI, there's a lot of noise in the space, a lot of hype in the space with LLMs and all this. But really my vision for it is a human-centered AI. So a probabilistic system that can inform geologists of plausible scenarios and integrate that sort of human expert interpretation with automated pipelines to better understand the subsurface in an interpretable and iterable way. So working together with humans or empowering geologists more in their regular workflows. Yeah, and thank you for having me here today.
Great. Anyone has questions online or here?
That's really great.
Yes, that's impressive. Could you elaborate? Okay, so let's suppose we've got a surface geology map and we have magnetic data. Right. So now you've got these 2 things that are, part and parcel of what you'd like to consider. How do you actually fold that into your sequence, and in particular actually both of those things, to try to get out something that's kind of matching your surface geology and would give a gravitational response?
Yeah. So the first step to do that sort of challenge would be in the simulation side of things. You would want to actually generate those 3D ground truth examples, but now also add whatever sort of forward operator you're seeing. So during the training phase, you would apply that forward operator like you're talking about. So if you have on top of surface gravity information, for example, so we need to run that in the simulation too. Then once you have that data paired with the 3D model, you run the regular conditional training process. One thing that we need to change is a way to find to put multimodal information in. So they're doing this with deep learning models right now, like in the example that I showed at the start of combining image and text, for example. So in this case, we would be combining like the surface data and some of the gravitational potential field data. One of the things that that we've done with this work is using that adjoint operator to try and enforce some type of consistency with the data that is being fed into the model. So the adjoint operator brings back the forward data, which is in 2D now. The adjoint will bring it back to 3D, and it'll bring it into the same sort of format as applying the adjoint to surface data. And then we would find a way basically to pair that in and embed that into the model as conditional information during the training. And then during the inference phase, we would just feed it back in the same way that was done during the training. And I would love to see the results from an experiment like that. So, yeah.
Are you getting close to being able to do that?
Yeah, I think so. I have some other research directions, but I would like to try that experiment as well. I don't think that there's too many modifications that would need to be done with this framework, specifically because the adjoint is there. You know, this is lithology, so you would need to have a handle also on some geophysical parameters in the simulation as well, I would say.
Is there time for another question, Tom?
Oh, yeah.
The models you show, geologic models you show, look particularly applicable to petroleum exploration. They seem to be, you know, you got layering. It looks like Phanerozoic geology to me. Have you been approached by petroleum companies, or have you approached them, or is there other people working in the same sort of field in the petroleum exploration business?
So I can say this type of simulation, the open source StructuralGeo package, you know, is being used by at least one person in the industry. I think a few. There's been some interest in it. There's interest, yeah, in petro applications as well, I'd say. Are you asking if I've been personally approached, like in regards to this work here? I'm not sure if I can comment on that. It is of interest, I'm sure.
I'm sure it would be.
People working.
Well, the corollary to that question is, what about mineral exploration? And here you're dealing with, you know, metamorphism, alteration, very complex geology.
Yeah.
Is, you know, this would have to be taken to the next level to be able to be used for mineral exploration.
Yeah, for sure. So that's part of the model fidelity, like I was talking about. So there's a lot of different mechanisms that could be put in place. Like one is having an expert opinion input. But I kind of alluded to it before with some of these transition probabilities, and there's a lot of probabilities. Like if I ask you, what is the probability in this area on Earth that a fault occurs after this type of fold occurred? And these are questions that don't really have answers to them. So one perspective to take is once you do have a simulation, the simulation itself has many different parameters in it, let's say, and it's a tunable simulation. The fact that it's a parameterized model, it offers almost a regularization in a certain sense. Like the range of geology that could explore within reasonable parameters is somewhat bounded. So if we could find ways to take feedback from our forward observations, because we do have a lot of those, in order to generate more realistic geology using this as a regularizer and just changing the parameters in this type of model, then this would be a constrained model and could show some promise for getting more feasible models. But it's certainly an enormous amount of effort when you start to get into it more of trading off exploration of diversity, because it's just so heterogeneous, geology on Earth, and at the same time remaining within plausibility and not having to get out of hand.
How sensitive to scale? I guess once you train your model, you said it's 128 or whatever, right? You form your cube.
Mm-hmm.
Is there a length scale baked in that idea? Can that 128 be like 500 kilometers or 1,000 kilometers, or is there like length scales basically?
Oh yeah, thanks for asking that question. That's a good one. So it's on a uniform grid. So the sample points are representative of a mesh cell, essentially. And the size of that mesh cell and the bounds on it is baked in during the simulation process. So those bounds can be changed. And basically, once you set the bounds, your resolution within that sets your mesh cell size. And so these models that I've shown here today from our work, it's implicit of what this resolution is that it's learning. There are other machine learning models out there which can do positional encodings, for example, and different ways of embedding this sort of information that's more explicit, that would be more friendly, let's say, to training at different scales or something like this. But as it is right now with this work, it's somewhat baked in of what the model expects to see should be at the same window size, let's say, and ideally resolution as what was seen during training.
And so what is your extent right now for these models? What would be kind of like the length scale that we're...
Oh, that's a really good question. About 8 kilometers by 8 kilometers, I believe. It's in the paper. I can't remember off the top of my head, but yeah, it's in that range. Yeah, so we're looking at 8 kilometers by 8 kilometers by 4 kilometers deep, I believe. Yeah. So it's we're putting a little bit of extra context window on the X and Y because it's very expensive. These 3D models, they scale with like ON cubed. It's not like pictures, which are very nice ON squared. This scales very badly. So we picked to have extra context over X, Y, Z, and maybe at some target depth.
You think you touched on it by saying like you wish you could like reuse these models. How far, like you always have to start from scratch, or can you kind of build off of one at all, or is it really specific? Kind of you have to retrain every time.
Oh, okay, yeah, the machine learning model. So within this framework, I mean, it could be an experiment to try and retrain modalities. The key question here is there's essentially, when you pass that forward data, that in itself goes through what's a smaller version of a machine learning model. And it encodes that data of whatever modality you have that's run through the adjoint. So it's at a fixed dimension, but it finds a way to encode that into features that are then injected into the larger overlying framework. So I think any work in that direction, you would want to put some type of control on that interface between the two so that there's some type of standard that it expects to see. And then maybe you could just retrain those elements that are the modalities that are going in. But as it is right now, it also has this implicit bias where it's really expecting to see the forward operator that you put in. So if you had some way to make it a bit more agnostic to whatever type of modality that you're working at, let's say your feature space has like more of a Gaussian distribution or something like this, then I imagine it could be possible. And I think there's likely work in this direction, you know, in vision models, for example, where they don't necessarily retraining all the time. Yeah, it's always better if you can reuse work that you've done for sure.
Hey Simon, thanks for the talk. It was really good. I have maybe 2 questions. One of them is kind of related to the comment you said before about giving a certain region of the Earth, or what like how faults or folding might happen and the probability of that. But also like tied to that question, can you enforce that in a physical way? Or for example, if you have a region of the world that has big strains on one particular side, like if you have a subduction zone, like east-west, and then you know that you'll have more contraction along that direction. Can you enforce that when you in the sequencing, when you select the next feature, the probability of the next feature? And also tied to that, what other processes are you I mean, have you implemented? And also if you're thinking about implementing, for example, are you modeling erosion or extension? Or for example, if you have, probably it's not applicable to this, but if you have ridges, mid-ocean ridges generating some crust,
Yeah.
are you considering those other processes?
These are all great ideas. You're hired. But no, more seriously, I will point out like this is one instantiation of a simulation. So the framework that I've shown today actually doesn't necessarily matter the model that you're using, right? So you could be using different models, and doesn't necessarily matter the simulation that you're using either. For this particular instance of simulation, it does have some limitations to it. It is open source, so it could be modified to put in some of those operations. It does have unconformities in it right now. Yeah, it's kind of a canvas to be painted, really. But in the sequence, like I showed, generally you have like the actual process itself, and then some type of randomization or like fuzzy G over it. So I can imagine it sounds like you have a specific area or type of sample that you're trying to model. So you could apply like these same principles, for example, to your specific case scenario. There's just a little bit of human work maybe involved in that one. Yeah.
Thanks.
I guess what Cynthia's saying is that the next process might not be fully random. It could be influenced by the.
Yeah. I mean, this is one, the Markov sequence, you know, is one way of approaching this in the interest of automation and pipeline, but you know, it doesn't necessarily need to be this simulation either. It could be some other one. Like it's just you want a lot of samples. The more diverse the geology is, the more samples too. You know, like the same in image processing. It's a much easier task to learn a generative model for human faces than it is to learn a generative model that just makes anything. You know, so.
That's a good question. Thanks, Simon. For the network, you had your A matrix. Is it right now expecting the exact same? So if that's for boreholes, for example, that's, you know, just a sparse sampling matrix.
Mhm.
Is that matrix fixed during training, or like if I add a new borehole, does that mess everything up, or can you change the A matrix as you go?
Yeah, so for this to be useful and to not retrain, again, back to that question, we would want to have like arbitrary borehole placement, maybe different numbers.
Yeah.
Right now, they're all vertical actually from this work.
Yeah.
But you know, it could be adapted different ones. I'll say a secret, this was interesting when I was doing this research. So the forward operator for boreholes is you just throw away everything else and all you know is like for one single borehole, you throw away the rest small and all you have is the same. And the adjoint for it is that you just bring back everything else, but it's empty.
Yeah.
Empty space, basically. So what this is like a masking operation when you have A transpose A in this particular case. But what that would look like if you had like a potential field or something more complex than that would be something different than just empty space around. But it is varying at each time during it. So it's implicitly learning, you know, that the boreholes could be at all sorts of different positions and it's not necessarily fixed. And if you want to go multimodal as well, you just do the A transpose A before passing in. The AM is of course forward data, so this is A transpose data, but you would do the same type of thing. So that it doesn't need to be fixed during training.
Thanks.
When you're doing your training, you're making you got simple models and then you're getting more complex and more complex. How do you know when to stop? You know, how do you know how complex is complex enough for what you want to do?
Yeah, so yeah, this is a tricky balance to strike. If you're training on general geology, then you do want actually to have some simple models in there. I mean, this is a point I didn't make at the start, but most of what we do know, actual ground truth examples, is where we've had like a mine or something like that. And so now most of like what we know, where we have boreholes and observations and things like this, there's been economic motivators there. And these are geologically anomalous regions, really. So for the simulation, the goal isn't actually to simulate all this. If you want just a broad geology, then really you want to explore that full space, including simpler geologies. So this is the Markov sequencing of variable times. Now, when it comes to longer, in this research, there's a cap on the total number of features put in, so it doesn't get totally out of hand or something at around 20. And then of knowing when to stop, it's part of tuning the parameters individually can be done and looking at visual examples, for example, and trying to find literature values for those random variables. It's a much easier task to manually tune each individual operation. Now, what they do when they're all mixed together, it's a much more difficult task to control. Ideally, you don't have too many outliers that aren't plausible geology. So the way of doing this is to just generate a lot of examples and start looking them through after tuning those Markov weights, things like that, or showing them to other geologists at UBC and asking like, hey, what do you think? Or we had some feedback on the 25 models that were shown here, you know, and if it's looking plausible, then it's trying to incorporate some geological prior, but it's an enormously difficult task to completely match things and ongoing work.
Okay, but here's a question. I mean, if you've got like, you know, some operator set that you're applying to some block.
Yeah.
What's an example of a, I mean, these are all very physical kind of things that happen in geology.
Yeah.
What would be a non-physical or a non-reasonable I guess, model that you end up with?
What do they look like, the non-reasonable ones?
Yeah,
You judge.
If you get like too many fold operators, so you have like a larger amplitude fold or something like that. I mean, there might be even some models that are going in that direction from in the 25 that are here. But it might just be. These might be some of the better
I'll do
looking
the
models.
work.
To be honest, I didn't put any that looked really bad in there, but I'm sure they do occasionally pop out. And the idea in training is that it smooths over, so let's see some of those. But as long as the general variety is like this, at point like when you start to get too much folding, you could imagine having like there's this surface topography, and there aren't really like water-based erosion events. So you could see having mountain forming events without the same type of erosion that would be happening to counteract that necessarily. So you can end up with like ridiculously large mountains, I'd say, is one failure mode.
okay.
Yeah.
Those are some kind of built-in Occam style, like, and, you know, we often say that the simplest model is that in the absence of knowing more, choose what's simple, right? Is there a way to bake that in, or?
Oh, simpler parameters. Yeah, it's an interesting question. I imagine more of this idea of being able to tune the parameters in some way, or there could be multiple sets of parameters to that. It'd be some type of regularizer or something like that is often what's seen in inverse problems, for example. But in this work here, it's again striking that balance between what is too simple and what's too complex. It's very easy to just generate the same really nice looking model 10 million times, and it's the exact same one, and then there's been no variety that's been explored. So it's finding that trade-off where there's not too many outliers, let's say, but that you're still
There's a lot of what we do, I think, in this group these days, we're looking undercover, and you might be in the middle of the Atacama in Chile, and there's 100 meters of gravel, and caliche, and often, like, you don't really know what's underneath there, right? When we do our survey, and you know, now we do some constrained inversions and get these big red blobs. And, you know, I guess the question I was that we should be able to do better than that, but we still don't have, you know, you may not have drill holes at the start. Is there a way to, if you didn't have drill holes?
Yeah.
Is there a way to, you know, I'm always thinking about how do we make our models more geologically reasonable when we really don't, you know, I guess what's reasonable is some concept in your head, not that we have, right? When you're undercover, there are no strikes and dips to map. There's no.
Yeah, super challenging. So I'm understanding your question more now is in the actual inverse process, like when you've put in the forward data and what comes out of them all. So I mean, the idea with this is that's been to explore more like the plausible models. So like you as a geologist with a lot of knowledge, or from your work that you do with a lot of knowledge from the field, right? You could look at, let's say, 50 different models, and they might look different. You're in that girl with the pearl earring scenario, but you have some domain knowledge that the model doesn't. And from what it's reconstructed, you can then select the ones that you think are the most plausible. So that would be the human input in this type of interaction with AI.